Okay, we're going to try one on continuity here, and we're going to talk a little bit about limits at infinity. So first of all, let's talk about continuity. We've talked a little bit about left-hand limits, which as x approaches a from the negative side, this would be a left-hand limit, and right-hand limits, as x approaches a from the right-hand side, this would be a right-hand limit. If those two things converge on the same value, in this case I've used another variable c, don't freak out. If they converge on the same y value, as x converges on a from the left and from the right, a limit exists. In this case, the limit is c. So, how is it continuous? It is continuous if the limit exists and if f of a also equals c. And let's talk about that for a moment in another picture before we go on too much farther. So let's go to these discontinuity graphs for a moment, and I'll talk about these. I'll just look at a couple examples. So here's one example here. All right, as you can see, as we approach x sub 0 from the left, this y value sits down here, so its left-hand limit might be something like 1. However, when we approach x sub 0 from the right, this y value comes up here, so in this particular case, the right-hand limit might be 2. Therefore, since the left-hand limit and the right-hand limit don't agree, this is not continuous. All right, picking another one, we could take a look at, how about this one right here? So, the left-hand limit as we approach x sub 0 here is 1. The right-hand limit as x gets closer and closer and closer to x sub 0 is also 1. The left hand and the right hand agree the limit exists. In this particular case, as we approach this value called x sub 0, which is 1, the y value also converges on 1. A limit exists. However, the function evaluated at 1 is 0. Therefore, the hole is not filled. So in this particular case, if we go back from this message, this part here was not satisfied. The limit exists, but the function itself was not defined at the exact same point. It was defined at 0, where these two both were 1. Looking at that one more time. These two both came to 1, but this one was defined at 0, not continuous. A layman's term for continuity is the fact that you can draw the thing without lifting your pencil. And here we would have to lift our pencil to draw the thing. So that's the basic concept of continuity. If we go far and look a little farther here, and I'm going to look at a screen snip from Desmos, this is another type of discontinuity called a vertical asymptote. Okay, vertical asymptotes generally happen when we have division by 0 going on. So if you'll notice, if I plug negative 1 up into this function up here, I have division by 0 going on. 1 over negative 1 plus 1 is 1 over 0. So if you'll take a look at the table, you can see that as we approach negative 1 from the left-hand side, here we go. Let's talk about this for a moment. As we approach negative 1 from the left-hand side, left-hand limit, then this guy here approaches negative infinity. It dives down to negative infinity. As we approach negative 1 from the right-hand side, it approaches positive infinity. The left hand and the right hand do not converge on one single number, therefore no limit exists. If no limit exists, we can't even talk about continuity. We definitely cannot draw this graph without lifting our pencil. This is not continuous. All right. One more quick example on here is the fact that from this Desmos, you got to be careful of rational functions. Not all rational functions have vertical asymptotes or discontinuities. If you'll notice, there are no values of x here that can be make the denominator equal to 0. X squared is always positive, and if I add 1 to that, I always get a positive number. So we can see here by the table, and we can see by the graph, that this graph is continuous at all these points. If we wanted to look at one specifically, as we approach, negative 1 from the left, this thing tends to a half. As we approach negative 1 from the right, this thing tends to the y value of the half. And also negative 1 evaluated at this function g of x is also the y value is a half. So since the left hand, the right hand, and the actual valuation of f of x at negative 1 are all 0.5, this thing's continuous, and I can draw it without lifting my pencil. Basic concepts here of continuity. If we go back, I'll show you the main types of discontinuities. A hole in the graph generally happens when we have division by 0 that can be factored out either by rationalization, removing factors, or perhaps some sort of working with fractions. A vertical asymptote happens when we have a non-removable discontinuity. In this particular case, the simple function 1 over x has a vertical asymptote. The last type of discontinuity is called a jump discontinuity, and a jump discontinuity happens when one side converges to a y value. So if it's y is 2 for all positive values, then the right-hand limit as x approaches 0 is 2, but yet the left-hand limit as x approaches 0 is down here at 1. Therefore, again, the limit's left doesn't equal the right. There's no limit exists, and if no limit exists, we can't even talk about continuity. Good enough for today.